While our senses ultimately arise from atomic scale interactions, we have seen that they are far from adequate for the task of detecting and distinguishing individual atoms. So if we are to construct history through atoms, we need to develop techniques to identify and count them. We have done this. We have machines that can take a substance, tear it atom from atom, and sort the atoms into individual boxes so we can count them. But unfortunately, that leaves the material under study destroyed. By using photons and neutrons, however, we can simply excite atoms in place where they are, or perhaps transform them into radioactive versions of themselves, and then, as they emit their characteristic particles and radiation, we can identify them without significantly altering the material in question at all. An obvious area in which such non-destructive techniques are invaluable is in studying works of art. Non-destructive analysis of a substance can reveal directly and unambiguously the atoms and molecules from which it is made. Neutron irradiation is one of the most powerful of these techniques. One fires neutrons at the object of study and either excites a nucleus to emit a gamma ray from a simple collision, or transforms the nucleus when it absorbs the neutron into a radioactive species of another element, which then decays on a predictable timescale. The great advantage of using neutrons over other subatomic particles is that they're neutral, and therefore they don't feel any force from either the orbiting electrons or the protons in the nucleus of the atom. And this allows them to get in close and comfortable. The first problem is to make free neutrons, because it turns out, while in the nucleus of an atom, a neutron can live for the age of the universe, if you take it out and set it on the table, a neutron has a half-life of only about 10 minutes. It falls apart into a proton, an electron, and an antineutrino. And so therefore, if one wants to use neutrons to examine things, like paintings for example, one has to generate the neutrons where the painting is. One can't put them in a bottle and travel across the state and walk into the museum and do it. So the painting goes to the neutrons rather than neutrons going to the painting. In order to maximize the likelihood of an interaction, one wants the neutrons to remain in the neighborhood of the particles they're interacting with as long as possible. Thus, rather than producing high-energy neutrons, which are moving rapidly and therefore zip right through the substance, one wants to slow them down so they have velocities that are comparable to the velocities, jiggling in place, of the target atoms, typically meaning they have energies of about 1/40th of an electron volt. Very slow neutrons indeed. Originally, neutrons were made by bombarding light elements with helium nuclei, such as helium colliding with beryllium, making carbon, plus spitting out a neutron. But these neutrons have energies of millions of electron volts because they've just been ejected from an atomic nucleus, and they must be slowed down before reaching the target. Furthermore, the maximum production rate of neutrons done in this way is about 10 million neutrons per square centimeter per second. That may sound like a big number, but when we see how unlikely it is for a neutron to actually hit its target nucleus, you'll see that falls far short of what we need. The advent of controlled nuclear reactors, fueled by radioactive heavy nuclei like uranium, greatly boosted neutron fluxes, that is, the number of neutrons we can get out traveling in a certain line for every square centimeter of painting for each second. And that number is now easily up to 100 trillion neutrons per square centimeter per second, 10 to the 14th. Now, that sounds like an overwhelming number, but it turns out it's really hard to have a neutron hit a nucleus. The reason is simple. You remember from lecture 1 that with the orange as the nucleus, the electrons were not, as they did in your textbook, orbiting like this, but they were orbiting 5 city blocks away. Thus, imagine firing something where the target is the size of an orange sitting in the middle of 5 city blocks. You'd have to throw a lot of neutrons down to have a chance of actually hitting the nucleus and not just passing through the atom. This target size is called, in physics, the cross-section. And the cross-section for neutron interaction with nuclei is incredibly low, 10 to the minus 24 square centimeters. A trillionth of a square centimeter for each square centimeter of canvas. Thus, we need these enormously large fluxes if we're going to generate enough radioactive nuclei that they can signal their presence. We should do a little calculation to limber up your mathematical ability with scientific notation and see why this is so. Let's say we have 10 to the 14 neutrons per square centimeter per second coming out of our reactor, and a cross-section of only 10 to the minus 24 square centimeters per atom. That means for each individual atom, even with 100 trillion neutrons being fired at it, there's only one chance in 10 to the minus 10 of the neutron actually being captured. Now let's suppose we have a painting that has in it some pigments that contain the element sodium. This will be one of the examples we'll be using. Say the painting has 1/10 of a gram of sodium in the particular piece that we're interested in studying. Well, we can calculate how many sodium atoms there are in 1/10 of a gram by simply knowing how many nuclear particles there are in sodium, 23 in this case, and the mass of each proton and neutron, which is a very tiny number, but a well-known constant of physics, 1.67 times 10 to the minus 24 grams per atomic mass unit, as we call it, the atomic mass. And so we divide that into 1/10 of a gram, and we find that 1/10 of a gram, just a few grains of salt, contain 2.6 times 10 to the 21 atoms. So now we multiply our 2.6 times 10 to the 21 atoms times the probability that each atom will actually capture a neutron, 10 to the minus 10, and we find out that some 2.6 times 10 to the 11th atoms, 260 billion atoms of sodium will capture a neutron and turn into the element magnesium. Now, this element of magnesium is radioactive, and it has a half-life of about 15 hours. Over 15 hours, you will recall, one half-life, it means half of those magnesium atoms will decay and emit the characteristic radiation, which will signal to us that sodium was in the painting. So, with 2.6 times 10 to the 11th magnesium nuclei, half of which decay in 15 hours, if we divide by the 15 hours and the 3,600 seconds in each hour, we find that we'll get a couple of 1,000,000 decays every second. Plenty of gamma rays to count for our detection. However, had the number only been 10 to the minus 7 as many neutrons as they were in the original production mechanisms, we'd only get a few or one every second, and it would take many hours to get an accurate measurement. Neutron activation consists then of a free neutron coming in and combining with an atomic nucleus to form a radioactive isotope. As in the process I just described, a neutron plus sodium-23 becoming sodium-24, which is then unstable and decaying to an excited state of magnesium-24 in a beta decay, therefore spitting off an electron and an antineutrino, and then relaxing, as all such decays do, to the ground state, giving off a gamma ray. It's the gamma ray we can detect. And because every nucleus, just like every atom, has a unique set of energy levels, precise and unique to it alone, the energy of the gamma ray, the transition from one level to the other, tells us immediately which atom was present. And so, if we see gamma rays of the right energy, we know that sodium was present in the pigments of the painting. Gamma rays are what come out rather than lower energy photons like light or ultraviolet rays, because the binding energy of nuclear particles is huge. It's millions of electron volts, and therefore a relaxation gives you photons with millions of electron volts. Now, this may not sound non-destructive as I advertised it in the beginning. After all, you're taking neutrons, you're firing them in, and you're changing the elements. Some of the sodium has now become magnesium, and it's decayed away. Clearly, you've changed things. Well, we have. But in this kind of experiment, when we have a painting and we fire hundreds of trillions of neutrons, we change so few of the atoms, it can't possibly make a detectable distance. The example is as follows. Suppose you had a warehouse that covered a full city block and was 20 stories high. And suppose you filled it with marbles, regular marbles. So a city block, 20 stories high, full of marbles. Those are the atoms of sodium in this painting. 7 would have been changed by this process. And surely you believe that if you have a warehouse that's 20 stories tall and a city block on each side, if you pulled out 7 marbles, it could hardly make a difference. So it is fair, I think, to call these non-destructive means of testing paintings. Each individual gamma ray can be captured and analyzed, so this very tiny fraction is sufficient. I have a few examples where these techniques have been used on real works of art to uncover forgeries, to reveal underpaintings, and ultimately to date things. The Spanish forger was an artist who maintained a whole workshop in Spain in the late 19th century and specialized in elaborating medieval manuscripts so they could be sold for higher prices. His work was definitively exposed by neutron activation analysis. One of the illustrated manuscript pages in question is from a 15th century Book of Hours. It was purchased by J.P. Morgan in 1900 and still resides today at the Morgan Library in New York City on Fifth Avenue. The borders are thought to be original, the illustrations around the edge of the writing, while the fancy illustration in the center of the page we can show to be a modern forgery. When this page was irradiated with neutrons, gamma rays from 9 different radioactive species appeared. The isotope half-lives had a very broad range. There was manganese at 2.6 hours, copper with a half-life of 12.7 hours, sodium at 15 hours, arsenic at 26 hours, gold at 2.69 days, chromium at 27 days, mercury at 47 days, antimony at 60 days, and zinc at 244 days. These different half-lives are critical for determining where in the painting different pigments were used. So the isotopes all undergo beta decay, emitting electron or a positron. What we do is put medical X-ray film smack up against the painting after it's been irradiated, and these positrons and electrons start coming off. And we leave it there for hours, or in some case for days, recording the exposure. The print we get when we take it away is called an autoradiograph. And again, the exposures last from a fraction of a day to several weeks. Each electron that comes off, or each positron that comes off, exposes the film in exactly the same way that film in old-fashioned cameras was exposed. Film consists of layers of silver halide on the surface of an emulsion, and when a photon of sufficient energy, or in this case an electron or positron, strikes one of those molecules, it breaks it apart, and that effectively exposes the film. So what one does is irradiate the painting, create all these radioactive isotopes, lay on the piece of film, and take it off after a day, wait a few days till some of the short half-life elements decay, lay on another piece of film, leave it on there for a few days, take it off, and continue this process throughout the year. The point is that while we can measure the individual isotopes by their gamma ray signatures, the gamma rays come off in all directions, and so we don't know where in the painting that particular element is located. By placing this film directly against the painting, the electrons come out and immediately strike the film. They don't have a chance to go off in other directions, and we can see where on the painting each of the isotopes is located. This has been done to this painting, allegedly by the Spanish forger, which sits in the middle of this true old manuscript. A series of autoradiographs was taken at 1, 5, 8, and 25 days after the irradiation. If you compare the first two panels, the blue flowers are seen to contain a copper-bearing blue pigment, a pigment that was available to medieval artists, in the border, while the blue sky in the inset contains a sodium-bearing pigment that was first synthesized in the 19th century, clearly something added later. Comparing panels 3 and 4 shows that the green border and the green in the flowers around the edge persists after the green fields in the inset have faded away, suggesting that the inset contains a green pigment, copper arsenate, that has a half-life of 12 hours and therefore after a few weeks is essentially gone, and this pigment was first made in 1814. While the border green is from some unknown pigment, but whatever it is, it contains some very long-lived isotopes because even after a month, it's still darkening the film successfully. That element could be chromium or antimony or zinc, which has a half-life of 244 days. The unambiguous conclusion, then, is that this illustration is a modern forgery inserted into an old manuscript after the beginning of the 19th century, and art historical evidence suggests that it is attributable to the Spanish forger and his workshop. This technique can not only identify the pigments in various parts of the painting, but it can allow one to see underpaintings that an artist has made over which he has painted another picture. My wife is an artist, and she does this all the time. She'll start a painting, she thinks it's not going well, she'll throw it aside for a year or so, one day decide she needs a canvas, pull it out again and said, oh, I don't worry about that, and just start painting oils over the top of it. That underpainting can now be revealed with neutron activation analysis. Van Dyck has a famous painting entitled Saint Rosalie Interceding for the Plague-Stricken of Palermo, which is a beautiful painting in the Van Dyck style. An autoradiograph, however, has shown that on the same canvas, underneath is a self-portrait of the artist. And I must say, having seen it, it looks too good to have painted over, but I guess Van Dyck was not satisfied with his initial self-portrait. In addition to throwing neutrons at paintings, one can also throw photons at paintings, in particular X-rays. And directly X-raying a painting allows one to probe the atomic composition of the painting without changing any of its constituents at all, because all one is doing is exciting electrons or perhaps nuclei with these X-rays. Now, X-rays can generally pass through a painting and the canvas on which it's painted, and they can be recorded on film or with a digital detector, much like dental X-rays are. Have you ever wondered how dental X-rays work? X-rays have wavelengths that are short, about 1/10 of a nanometer, about the same spacing of atoms in a solid. Therefore, while visible light can't shine through my teeth and be detected by a camera inside, the X-rays just wiggle so quickly they wiggle right between all the atoms and can be recorded on the film. Again, the X-ray energy is used to break apart the silver halide or whatever other molecule is used and expose the painting, expose the film. My dentist now has moved to digital cameras, as most people have in their everyday life, and puts a little computer chip in my mouth when he shines the X-rays in on my cheek. The little computer chip, like the one in your digital camera or your cell phone, consists of tens of thousands of little wells, little electronic wells, in which, if stimulated by an X-ray, a bunch of electrons collect, and then, on command, electronic signals have these little piles of electrons bucket brigaded down until they read out as a signal, and therefore you can tell where the X-rays were absorbed. The electrons closest to the nucleus of an atom can be excited or even ejected by absorbing an X-ray because, again, the binding energy of those inner electrons are hundreds to thousands of electron volts, the range of X-ray energies. Given the unique binding energy of each electron in each type of atom, the energy of the X-ray absorbed reveals precisely what kind of atom is involved. For example, lead white, something that one often primes canvases with, absorbs at 0.071 nanometers, and if that wavelength is missing as the X-rays pass through the painting and through the canvas on the other side, one knows that lead white must have been in the painting. X-rays can also excite electrons, which then fall back to their original orbits, re-emitting the X-ray of an energy characteristic of that particular element. Comparison between the spectrum of the emitted X-rays from a verified work for a particular artist, something that you know was actually painted by that artist, can, for example, reveal whether other putative works by that artist are real or fakes, because the exact combination of pigments and pigment suspenders and varnishes and everything else that one artist used is very unlikely to be the same as what another artist would use. Also, being able to tell from which parts of the painting the X-rays emerge can reveal touch-up work that was done at a later period or painting over an original work. Finally, shining ultraviolet light on a painting can make the surface layer atoms fluoresce. Fluorescence is a peculiar property of some kinds of atoms, where atoms in the outer energy levels get bumped up to a higher level by, say, ultraviolet light, but then, because of the particular arrangement of the energy levels of the atom, they get trapped there. Rather than existing only for fractions of a microsecond before they fall down, they can sit there for a long time, hours or even days. So UV photons excite electrons up to these higher levels, which eventually fall back down, giving optical photons, visible light, light that we can see. Linseed oil and varnish, for example, both fluoresce very efficiently. As varnish layers oxidize, that is, combine the chemical composition of the varnish with oxygen atoms from the air, the molecular structure changes, and as a consequence, the fluorescence yield declines. You get fewer of these photons back for the ultraviolet light that you shine on it. This technique has been used to show, for example, in some Rembrandt paintings, that there are 4 separate layers of varnish layered on at different times, separated by many years in some of this artist's work. Cave paintings are another kind of art that we would like, of course, to know more about, because unlike regular paintings, they're never signed, and they're usually never dated either. The most pressing need for cave paintings is actually not to determine whether they're forgeries, because of course we don't even know who the original artists are, but to date them. And, unlike normal paintings, we can't take them to a neutron reactor. They're stuck in the wall of the cave they're in, and we can't bring the reactor to the cave. But we probably can, in the case of these large cave paintings, afford to fleck off a little fragment of the painting and take it to the laboratory for analysis. This is, in general, challenging because our standard dating technique for things that are tens of thousands of years old is using carbon-14, as we have mentioned before and we'll discuss in the next lecture. And carbon-14 doesn't work on the inorganic dyes that are used in most cave paintings. However, cave artists often used organic materials like blood and eggs and seed oils and plant resins and milk and honey and fat to mix with their pigments as binders and to help the pigments stick to the walls. And so some of them can be carbon-14 dated. Unfortunately, it's a little tricky to do this, however, because these paintings are often on limestone caves. Limestone is the substance CaCO3, calcium carbonate, calcium, carbon, and 3 oxygen atoms, and that, of course, contains carbon. Calcium carbonate is from the microscopic shells of foraminifera, little plankton that live in the ocean, which accumulate on the bottom of the ocean and then, as a consequence of tectonic activity, end up on dry land in caves. That carbon is very old, tens of millions, hundreds of millions of years old, and as a consequence, all of the carbon-14 that was ever in those little organisms when they were alive has long ago decayed away. So when one scrapes a little painting, cave painting, off a wall, one inevitably gets with it some limestone, and as a consequence, one is mixing very old carbon, from which all the carbon-14 is gone, with the young carbon, relatively young, a few thousand years old, of the cave, of the painting that was put on the wall of the cave. Some clever people have figured out a way around this, however, to isolate the pure organic carbon. You start with a vessel that's very tightly sealed and creates an excellent vacuum, and you attach to it a vacuum pump. And you pump out all the gas molecules that are in there that you can, down till there's less than 1 part per billion of a normal atmospheric composition. You then add absolutely pure oxygen gas, to this substance to attract the carbon atoms to make carbon dioxide and the hydrogen atoms to make water from any contaminants that are left on the walls of the container, on the seals, on the pump oil or whatever, and flush the system again, pump it out again. You then take this paint chip from your cave wall, or perhaps a shard of pottery from the floor of the cave, and you put it in the container, add pure oxygen again, and heat it to about 100 degrees centigrade, about the boiling temperature of water. You will again, out of that shard of painting, get carbon and hydrogen released, and so again will form carbon dioxide and H2O, water. To separate these two, you slide in a finger that's at about 0 degrees, so water freezes on it, and all the water molecules find this cold finger, stick to it, and make a little layer of ice. You withdraw it, and all the water vapor is gone. You then stick in another finger, but rather than cooling it just to 0 degrees, the temperature at which water freezes, you cool it with liquid nitrogen to something like 320 degrees below 0 on the Fahrenheit scale, which is cold enough to collect all the carbon dioxide as well. You then pull that carbon dioxide out. You add to the carbon dioxide hydrogen gas, and that makes H2O, the oxygen goes with the hydrogen, and the pure carbon is left behind. Typically, this process yields about 12 milligrams, 12 thousandths of a gram of carbon for every gram of material that you put in. You then use this pure carbon from the substance itself for carbon-14 dating, which we'll explore in detail next time. The contamination in this process, according to the authors who did the experiment, is very low. They believe they have cleaned the chamber so that the contamination is essentially 0. the contamination from organic material that might have stuck to the painting after it was done, rain that fell onto it, mud wasps that stuck to it or whatever, they estimate as less than 5%. But most importantly, the principal source of contamination one is worried about, the calcium carbonate or limestone that the paint was stuck to, is zero, or at least less than a few percent, because the carbon in calcium carbonate won't be liberated until the temperature is above 200 degrees, and you only baked this paint chip to 100 degrees. So that carbon remains safely locked away. That old carbon, which would contaminate your measurement, is taken out of the equation. In West Texas, a cave painting was dated this way, whose origin was unknown to at least 1,000 years, and the answer came out 3,865 plus or minus 100 years. That is, almost 4,000 years ago, we can tell which century this painting was done. A lower limit on a cave painting's age can also come from deposits that are put on the painting after the wall was painted. Mud wasps are a favorite example. Mud wasps build these nasty little pyramidal nests of wasps, which they carry in their mouths and stick together until the nests become very large. It can contain thousands of wasps. As the wasps sweep up this mud, they inevitably incorporate little grains of pollen from the time the nest was built. The little grains of pollen, of course, are rich in carbon-14, being organic material, and the carbon-14 begins decaying away as soon as the pollen enters the mud wasp nest, because the grain is no longer alive. This gives you a clear date when the nest was built, which tells you a lower limit to when the painting was made, because clearly the mud wasp nest was installed after the painting. Furthermore, an analysis of the type of pollen grains present, something not so difficult to do, gives you simultaneous information on the climate at the time that the mud wasp nest was built, perhaps somewhat after the painting was made. A well-known Australian cave painting has been dated in this technique to be more than 17,000 years before the present, because the mud wasp nest was of that age. Using neutrons and photons, then, to excite and transform atoms, we can non-destructively manipulate works of art, both prehistoric and historic, to yield information on their provenance. Using naturally occurring radioactive nuclei provides an even less invasive approach, of course, to reconstructing the history of human artifacts. And this is the approach we will explore in the next lecture.